My name is Chang Hwan Kim and I'm from Hydrogen Energy Technology Laboratory at the University of Michigan. Today, you might have noticed that I rephrased my title a little bit to make it concise. I'm going to talk about the influence of oxygen mobility for the deactivation of some pretty cold water gas catalysts using isotopic exchange experiments. So the first part of my talk will focus on deactivation and reaction mechanism of the supporting cold catalyst to discuss what would be the ideal way to stabilize and manage the activity maintenance, and also how it is related to associate with the surface oxygen mobility for the cold catalyst. And with the given information, I will also talk about the influence of oxygen mobility to the deactivation behavior on the severe zirconia support on cold catalyst. So as you may know, the water gas shift reaction has been used commercially for the hydrogen production. Water gas shift reaction is used to remove the CO, carbon monoxide, which is toxic and also poison the some types of applications such as electrocatalysts for PM fuel cells. In the water gas shift reaction, the CO and water reacts to produce the CO2 and extra hydrogen. But as you can see here, the reaction is thermodynamically equilibrium limited at the given reaction conditions. So commercially, they have two different stages of reaction, the high temperature shift and low temperature shift. And commercially, the iron chromium catalyst has been used for high temperature shift, but it has a lower intrinsic activity. And copper zinc alumina catalyst has been used for low temperature shift, but it has a stability problem during the reaction. So it caused those drawbacks. It caused the large volume of water gas reactors in the fuel processor to generate the hydrogen. So it is very important to develop the very highly active and highly stable catalyst for water gas shift reaction. Since after the Haruta reported the gold is very active for CO oxidation, even at the very low temperature, there are a lot of different reactions that have been used with the gold catalyst. In 1996, Dr. Andreva also reported that iron oxide supported gold is active for water gas shift reaction. And our group recently reported that the gold catalyst is much more active than commercial copper zinc alumina catalyst. And as you can see here, initially the 5% gold on Syria was almost 5 times more active than copper zinc alumina commercial catalyst. However, it is very susceptible to deactivation, and it lost almost more than 50% of initial activity after 10-hour time on screen. So we tried to find out what caused the deactivation and to determine the deactivation mechanism during the reaction. So first of all, we tried to observe the morphologically on the gold surface. As you can see here, the fresh gold catalyst has a very clean surface. Unfortunately, we don't have the in situ transmission electron microscope available in our institution. So what we did was we took out the sample grid and put it in the water gas shift reaction stream and soak it for about 4 to 12 hours and put the grid back to the TM instrument and tried to find the same particles that we believe is the same region. As you can see, after the 12-hour deactivation, you can see the amorphous layer has been developed on the clear gold particles. And we attribute it as carbon monoxide, carbonaceous species such as carbonaceous or formates by looking at the in situ XPS. And as you can see here, from the fresh catalyst, there is not much the carbonaceous species was observed. However, after deactivation, there were some type of carbonaceous species was formed on the surface. In addition to in situ XPS, we also use in situ drips experiment to observe the further evidence of the formates and carbonate species. We pre-treat our fresh materials at a 4% hydrogen in the nitrogen at 200 degrees Celsius, as we do typically for the activity measurement. And then we soak the catalyst in the CO and water stream, which is the reactants for water gas shift, and monitor what kind of the species was observed on the surface. As you can see, pretty much a significant amount of the formate and carbonates are observed on the surface. And as you can see, the gas phase, the CO2 and CO is also observed during the while we are flowing the reactants over the catalyst. So after the 1 hour soaking in the reactant stream, we switch the gas to the inert nitrogen gas to purge it out, both the gases, the products, and also as well also the species which was observed on the surface. As you can see here, the formates and carbonate species are not easily removed in a 1 hour purging. At 2 hours, there are still quite a bit amount of the carbonate and formate species are observed on the surface. After 15-hour purging, it's quite a bit of a long period of time, but still there are some carbonate species was observed on the surface. So possibly these carbonate and formate species must be the main blocking species on the active site. So we try to determine then what would be the ideal way to inhibit the or maintain the better activity. What would be the best strategy to improve the activity maintenance? If the formate and carbonate species are just spectator, which means just a byproduct during the water gas shift, then we probably might be able to suppress or inhibit the formation of carbonate formates by leaving the active sites available during this reaction. However, if the formates and carbonate species are intermediate species, which people call it the major actors during the reactions, then if we inhibit the formation of formate and carbonate species, probably our rate will go down as well. So, to determine what is the role of the formate and carbonate species, we investigate what kind of reaction mechanism the gold follows during the water gas shift reaction. As most of you know, the water gas shift reaction follows has been suggested following the two reaction mechanisms. They are still under debate in the literature, but the redox mechanism is the water dissociates under reduced catalyst, and the water dissociates into hydrogen and oxygen and absorbs CO, take the dissociated oxygen to produce CO2 and hydrogen. In the case of formate mechanism, the absorbed CO2 takes the hydroxyl from the water to produce the formate, and it is then decomposed to CO2 and hydrogen. One of the way to determine which the mechanism that the gold follows was to use the Kennedy experiment to see what kind of model fits well to the water gas shift reaction for gold catalyst. So we use the typical microreactor system to change the reactants at different partial pressure level. The reaction condition is listed in this table, and we use the 26 partial pressure variations at the 3 different temperatures. So total, the 78 points of data were large enough to fit most of the model that we evaluated. So the first thing we did was we set up the simple redox model to see the gold follows the redox mechanism. As you can see here, the water dissociates on the reduced site of the gold, and then the CO2 produced from the CO and oxygen from the support. And in this rate expression, you can clearly see the rate is pretty simple, and it is totally independent from this partial pressure of CO2 and hydrogen. However, when we fit the data into the model, here the pink square illustrates the experimental result, and also the green circle is for calculated result. If you look at the Perry plot, The experimental data was not independent from the partial pressure of CO2 and hydrogen, which means it might not follow the redox mechanism. And there's another evidence that, as you can see in this reaction pathway, if the water dissociates on the surface, if we inject a small amount of water on the surface, it probably have to release some types of hydrogen from the surface. So we first injected the little tiny bit of the water at the 24 degrees Celsius. But as you can see, as we press the water, the mass spectrometer showed that there was not hydrogen produced from the surface, which means the water does not dissociate on the active surface. So other than the redox model, we also listed all types of different Langmuir-Hunsrud types of reaction model, kinetic models. As you can see here, the single site represented, there are the sites which the CO and water absorb at the same place. And your site is representing that the CO and water is not necessarily compete each other to observe on the same site. So they have two different sites. So with the given this reaction models, only the experimental data only well described by the one specific model, which is the dual site surface reaction limiting model. As you can see in this Perry plot, in contrast to the redox mechanism, the rate was well expressed with the partial pressure of the CO2 and hydrogen. So as the partial pressure of CO2 and hydrogen increases, the rate decreases. So this was one of the best fit we could evaluate out of the different models. So if we interpret this model, please note that the site for the CO absorption is different from the site desorption of the CO2, which is suggesting that the gold may have some types of intermediates present on the surface. So this may be a kind of the evidence that the gold follows formation mechanism. So having the illustrated research, kinetic experiments told us the reaction follows the formation mechanism, and the activation is due to the accumulation of carbonate and formate species during the reaction. Then what would be the best way to enhance this activity maintenance on the oxide, the golden, the cerium oxide support? One of the strategies that we came up with was the accumulation of the carbonate species may be inhibited by the modifying its surface properties, such as the surface oxygen mobility. So, speaking of the surface oxygen mobility, zirconia has been known to enhance the surface oxygen mobility on the cerium oxide support. Actually, the Fornaciero and Marducci recently used the computer simulation to prove that the zirconia enhanced the surface oxygen mobility of cerium oxide in the late 90s. With the given information, we prepared the Syria zirconia solid solution for the gold catalyst. And as you can see here, the cerium oxide by itself and Syria zirconia solid solution gave almost the comparable activity initially. However, after 12-hour deactivation, the activity maintenance was totally different from the cerium oxide support by itself. As you can see, when you measure the R/R0, the case for the Syria zirconia supported gold catalyst was almost twice as much as the Syria by itself available on the gold catalyst. So having these results, we tried to characterize these materials using different methods. And one of the best methods to illustrate the difference in mobility between the two materials will be the oxygen isotope exchange experiments. Actually, this measurement was first introduced by the Winter and Borisov in the late 50s and early 60s. In the mechanism, like previous speaker illustrated, the oxygen 18, the dissociative absorb on the surface, and they migrate on the surface, and the exchange of the oxygen 18 and oxygen 16 occur and represent how the mobility of the surface was. So to monitor the amount of oxygen 18 and oxygen 16, we modified our commercial surface characterization instrument to have closed loop, the fixed volume system. As you can see, we had a fixed volume with a closed loop in this instrument, and we since the exchange rate for the isotope oxygen was relatively slow, so we circulated the fixed volume in the closed loop by injecting a little bit of the oxygen isotope in the inner system. So as we recirculate the volume, the flow, we injected the 5-6 sample loop. Using the 5-6 sample loop, we injected about 1 to 4 millibar partial pressure of oxygen into the system and monitored how the level of each oxygen 16 and oxygen 18 changes in time on stream, as well as the different temperatures. So the first thing we performed was we injected 1 millimole of the oxygen 18 into the system. 1 millibar of the oxygen 18 corresponds to 15% surface coverage of the monolayer. And as you can see, the oxygen 18 is quickly absorbed on the surface. And as you see, we observe the oscillation because we are recirculating the closed loop. So as we inject the oxygen 18, it was the mass spec takes the sample at a certain period of time, and that's where the fluctuation was occurred. But however, after a couple of after some time, it was diluted and diffused through the closed system. So as I said, the oxygen 18 was quickly absorbed on the surface. However, the oxygen 18 was not fully or equimolarly absorbed from the surface. For the case of the zirconia chromatic cerium oxide support, the behavior of the oxygen 18 absorption was similar to what we saw in the cerium oxide by itself. However, the exchange rate was much higher on the zirconia chromatic cerium oxide support. So when we calculate the exchange rate, the rate was significantly different from each other. So after that, we also did how the total amount of exchange, the oxygen 18 changes as a function of temperature. In this case, we injected 4 millibar of the isotope oxygen and we circulated for about 1 hour because, like I said, the exchange rate is relatively slow, so we wanted to make sure everything was exchanged it reached equilibrium at a certain temperature. So we increased the temperature from room temperature to the 500 degrees Celsius. As you can see, the oxygen 18 was started absorbing around the 100 degrees Celsius. However, the oxygen 16 from the surface did not start exchange until 300 degrees Celsius, which is way beyond the operation range that we run for the water gauge situation. For the case of Syria zirconia, the absorption was similar to what Syria alone provided. However, the exchange amount of oxygen 18 was pretty much more than what we saw from the cerium oxide support only. So this one illustrates that the zirconia promoted some types of surface oxygen mobility on the cerium oxide support. And similar trend was also observed with the nanoparticles on the both support. So this visual illustrates that. So instead of having the CO to form formate and accumulation of the formate and carbonates, probably by having some increasing the surface oxygen mobility of the support material by adding the zirconia on the cerium oxide, we might be able to achieve some type of easily decomposed CO format in the surface to suppress the deactivation during water gets shipped. So the isotope oxygen exchange results illustrate that the zirconia increase the oxygen mobility on the serial surface, and also enhance the activity maintenance for could be due to the enhanced oxygen mobility. So the enhanced oxygen mobility may have been reduced the accumulation of formate or carbon species. So this one illustrates that the isotopic exchange experiment could provide us a good probe for measuring the oxygen mobility for different oxide support. So I'd like to thank the Thompson Research Group and Hydrogen Technology Laboratory for giving us the great opportunity for doing this research, and Paramount Energy for funding this research. Thank you very much.
It is open for questions.
Yes, my question is...
Take the microphone.
Okay.
Yes, my question is, you're saying that the OH groups are on the gold cluster. I guess there have been some in situ Zane studies that have shown that the gold is mainly metallic under water gas ship conditions. I'm wondering if maybe the OH groups are actually associated with the defects on the ceria, and so the formate and the OH groups are on the ceria, and the gold is helping to extract the hydrogen from those species. And in that case, I think it's very interesting that basically what you're showing would be that increasing the oxygen mobility is increasing the mobility of those oxygen-containing species. So the formate molecule, since it's bound by its oxygen atom, is actually moving faster on the surface. Is that correct?
Yeah, that's right. But like you give us comment, if I put a cartoon that the water dissociates on the gold particles, I mean there is a gold could dissociate on the interface of gold and the support. So that cartoon was just illustrating two extreme cases to show how the difference between the reduction and forming mechanism.
Leon Leffers, Twente University in the Netherlands. I have basically two questions. The first question would be, did I understand correctly that you were claiming that the carbonate species would be on the gold particles?
Well, based on the morphological observation study, there was carbonaceous amorphous layer was built on the gold surface. So possibly that the carbonate species might migrate to the gold surface. But there is no kind of other evidence that we could tell the carbonate is only deposited on the gold surface.
But the preferred position of the carbonate species would be on the ceria.
Yes, because the CO2 is always formed on the cerium oxide by itself too. So carbonate is also formed the cerium oxide without gold particles. But in our system, possibly it could be in the interface, and only we saw the amorphous layers because probably it migrated into the gold surface. But you're right, probably they could be stuck on the cerium oxide support.
The second question directly correlated to that. Wouldn't it be a much more easy explanation of your results if you add zirconia, simply by realizing that carbonates on zirconia are much less stable, and the zirconia would simply have the function of helping the carbonate to decompose?
Yes, that's right. But we didn't try the zirconia by itself because we usually get the better, higher surface area on the cerium oxide. So if we add a zirconia on ceria, it was not as much as active. If you calculate based on the weight-based rate, it was really hard to compare to the rate we got it from the cerium oxide.
So maybe you're welcome to try. We did some work on platinum on both supports as well, and we know for sure that in zirconia the carbonates are unstable.
is about your size of your particles that you showed. They seem much larger than the typical gold size.
That's a good point.
You would need.
Actually, when we did the ex situ, I call it the TEM experiment, the morphology observation, we collected the many different particles from the fresh catalyst. But once we treated it, we took it out and treated it in the different water gas reaction and put it back to the TEM. Most small particles were deformed or was hard to be identified. Probably due to the small particle is more active and might have built more thicker the layers of the carbon. That's one of the particle which we could tell easily we are looking at the same particle, which is a higher, larger particle. So mostly when we look at that, the singular particles are always larger.
Really, that comes down to, because microscopy always looks at a very small region of the sample. That picture that you showed, do you consider that to be the typical gold particle, which is active for this reaction?
Yes, it is not the most active particle, but I'm sure the particle in 10 nanometer is still active.
From the University of Belfast. Can I ask one question first of all? If you remove the carbonates and formates, do you recover the activity of the catalyst right back to the original state? So if you remove the carbonate and the formate, which are causing, according to you, the deactivation, do you get back to the original high activity?
That's a very good question. Actually, I have the express part of how the activity changes. First of all, once we could remove all the carbon and species by adding some regeneration process, we reported this on the journal analysis a couple of years ago. After we observed the carbon species, we raised the temperature up to 400 in air, and we pitched the sample, and we could remove all the carbon species here, and the activity was fully regenerated here. The ion spectra that I showed you today was there's still a little bit of the carbon remained. So I also did the exact same purging procedure for the catalyst. So after I ran the deactivated catalyst, I purged with nitrogen in the reactor and measured the activity again. And the deactivated catalyst was regenerated afterwards, but not fully because of probably due to the residual carbonates formed on the surface. So the degree of the regeneration was different from how we treat or how we purge on the surface.
Because the other thing you've not mentioned at all is any interaction between the gold and the oxide support, which I think most people think is very important. And if you break that interaction, many people would think you also can lose activity.
Well, actually, I noticed that the speaker presents tomorrow or have a very interesting research on the interaction between the gold and Syria. We have not considered that effect, but I would love to know if that can be applicable on this observation that we have.
Okay, one of my colleagues, Chris Hardy, will present later in the week some very nice extracts and XPS, high pressure XPS information, which I think is very relevant to that point.
Thank you very much.
Right. I think it's getting close to lunchtime, so let's thank us.